next speaker is Sheehan, who's going to go into infinity and beyond. And he's from Imperial College London. Over to you.
All right, thanks. And this is all joint work with Marcus, who I guess is your colleague in Manchester. And actually, it's from his PhD thesis, which he did here in Cambridge. And while the title is probably maybe more grandiose than the actual talk, but to be more precise, what we're going to discuss, since we only have 30 minutes, and it is very relevant to Wiener-Hopf. So we're going to consider the problem of given templates matrix, and let's allow it to be block templates, compute its matrix factorizations, either a UL decomposition or QL. We won't talk about the standard ones like LU or QR because those are a lot easier and we only have 30 minutes. And of course, for those experts in the room, UL is Wiener-Hopf, or can be solved exactly with Wiener-Hopf. But we're going to look at, rather than sort of the analytic solution, the sort of numerical computation of these factorizations. Okay, so for most of the talk, we'll sort of think of things as templates or block templates. We will allow finite perturbations. So imagine a finite rank, or actually a finite dimensional perturbation of these entries, and compute the factorizations for that case as well. So essentially, we only are imposing that the tail, as we go to infinity, is templates. The actual finite dimensional entries might differ. Okay. So that's the question of the talk. We have 3 sections. We'll first start with some motivating applications. One's different than the usual Wiener-Hopf applications. Then I'll discuss UL, which is of course solvable with Wiener-Hopf techniques, followed by QL, which I haven't seen in the Wiener-Hopf literature, but if it's very likely it does exist, so please let me know after the talk. Okay. So what kind of applications are we interested in, and why do we want to work with infinite dimensional operators rather than finite dimensional matrices? So the typical question you might ask is, so let's take a discrete Schrodinger operator and add a potential. So this would be like a semi-infinite operator, which we've truncated to make a finite dimensional matrix. So this is templates plus a finite dimensional perturbation, and we want to compute the spectrum, in particular the discrete eigenvalues. So if we take a finite dimensional matrix, we get a bunch of eigenvalues here accumulating on the continuous spectrum of the infinite dimensional operator plus the isolated discrete eigenvalue. Okay. Now in finite dimensions, we can compute eigenvalues very efficiently using either the QR algorithm with shifts, and so we can get very fast and accurate values for these eigenvalues of this matrix, or we can use something which is essentially the exact same thing, which is the QL algorithm with shifts. Our goal is, rather than discretize and compute spectrum, this is our application, we won't go into too much details about it, but just to motivate why we want to do infinite dimensional factorizations, we want to instead compute eigenvalues of the infinite dimensional operator without truncating, in which case we can replace the finite dimensional QR with an infinite dimensional QR, or the finite dimensional QL with the infinite dimensional QL. So both of these are algorithms built on top of factorizations. If we can do the factorization, we can do the eigenvalue algorithm. We want to be able to do these infinite dimensional algorithms. And the reason we want to do QL rather than QR is the way shifts work for QR iterations is you sort of look at the entry in the bottom right, and this gives an estimate for the eigenvalue. In infinite dimensions, there is no bottom right. So the reason we want to do QL and not QR is to compute spectrum, compute this eigenvalue, and in order to do shifts, we have to do QL, which puts the sort of estimate of that eigenvalue in the top left rather than the bottom right. So hopefully that's clear. Now, why not just use this eigenvalue for the truncation as an approximation for the true eigenvalue? And this actually works very well for this simple problem. If I do this, approximate the spectrum of A with, say, 1,000 by 1,000 discretization, it works very well. This is 2.5, and this is 2.5 plus 10 to the minus 16. So for the simple problem, there really is no reason to use infinite dimensional algorithms. But if we do something a bit more complicated, let's, for example, think of a Schrodinger with periodic potential. So we're taking the discrete Laplacian, adding plus or minus 1 on the diagonal. This is a Bloch-Laurent operator. We can reorder things so it's block templates. So this is a block templates operator. And we can do this either in a 1D or 2D setting. So the motivation for trying to do things in infinite dimensions is if we do the standard technique of truncating and computing eigenvalues, we get this phenomenon. We get something called spectral pollution. So in 1D, it actually still works fine. But once we get to higher dimensional operators, there should be a gap here. But the gap is filled in by fake eigenvalues, false spectrum. So if we are able, for this 2D problem, well, to get to the point, we're not, but if we were able to do infinite dimensional matrix factorizations, we could compute eigenvalues that live inside this gap and avoid the spectral pollution problem. So that's the ultimate goal. That's the motivation for trying to understand infinite matrix factorizations on a numerical level. And if we add in a perturbation to our Schrodinger with periodic potential, that creates discrete eigenvalues that can live in this gap. Another issue that also comes up in 1D is if these discrete eigenvalues get too close to the continuous spectrum, their accuracy breaks down. Where if we were able to work with infinite dimensional QL, we could compute these eigenvalues arbitrarily close to the continuous spectrum. Okay. Okay, so that's generally the motivation. One other motivation is going beyond symmetric positive definite operators. We can consider a non-self-adjoint templates operator along with perturbations. And a classic example has this very simple symbol here. And again, if the spectrum of this operator is inside the symbol of the operator, if we did a finite section, we get eigenvalues that look like this, and where an infinite dimensional problem would see the whole spectrum. Okay. Or another case where this is useful is computing embedded eigenvalues. So imagine you have a templates operator like the last one and add a perturbation. That perturbation can introduce an eigenvalue inside the continuous spectrum. If you did a finite section, if you did a finite section and only look at the eigenvalues, you'll never be able to tell which ones corresponds to the eigenvalue and which one corresponds to the spectrum, which one has sort of a L2 eigenfunction attached to it. Okay. Where the infinite QL, actually, we'll see some examples at the end of the talk where we're allowed to sort of peek inside the continuous spectrum and compute eigenvalues that are embedded. And we need to be able to work with infinite dimensional factorizations in order to do this successfully.
What is L11? What is it?
The 1-1 entry of L.
Say it again.
The top left entry of L.
Okay.
So lambda is sort of the spectral parameter. You compute a QL of A minus lambda I. This is like a quick and dirty QL algorithm, is you just do root finding on L11. And that tells us where the eigenvalues are, both outside the continuous spectrum, but also inside. So there's a subtlety here. Okay. For something a bit more real world and perhaps interesting to the Wiener-Hopf experts in the audience is you can have this sort of phenomenon of embedded eigenvalues if you, say, have a Laplacian in a channel with an obstacle where you can have sort of trap modes, eigenfunctions that live here whose eigenvalue is inside the continuous spectrum. And when we discretize it, let's say we do a finite difference discretization of this, at infinity this looks exactly like a block templates operator. So this is actually a special case of our block templates plus finite perturbation. The finite perturbation is coming from here, and then the block templates is coming from there. Okay. And this is sort of things people struggle with. There are very good numerical methods for computing eigenvalues, embedded eigenvalues, but it's still a challenge. Okay. I won't have time to talk about this, but the other reason I'm interested in it is it allows us to take an orthogonal polynomial family and modify its weight with a rational modification. But I won't go into any details of that because of time. Okay. Okay, so that's the sort of motivation, which is slightly different from the standard Wiener-Hopf community, at least as far as I know. So let's look at the classical case, which I'm aware that I'm speaking to people who know this stuff much better than I do. So apologies if I say anything wrong or right, but that's silly. I apologize if I say anything wrong. But let's start with a simple motivating example, which is let's consider a simple tridiagonal Toeplitz matrix. And essentially our numerical goal is to compute its UL factorization. Okay, I won't say, I'm going to stick to tridiagonal for the most part in this talk, because rather than look at, so nothing I say really applies to general Toeplitz. It does apply to banded Toeplitz, because a banded Toeplitz operator is equivalent to a block tridiagonal Toeplitz. So for the most part, I'll stick to tridiagonal with the view that here we have three scalar entries. These could potentially be blocks. And that's enough to capture general Toeplitz, banded Toeplitz matrices by just embedding it in a bigger block size. Okay, so the question is, this is our symbol. We want to compute the UL. This is a particularly degenerate example because we're right on the edge of the spectrum. But the UL decomposition is still well defined. Okay. So we want to compute the UL decomposition of A, but more generally, A minus lambda I, where let's say we shift away from the continuous spectrum. But ideally, we want something that's robust as lambda approaches, in this case, 0, as we approach the continuous spectrum. Okay. So there's lots of ways we could do this. This is a scalar problem, so we could use the exact solution formula in a numerical way. We can recast this Wiener-Hopf problem as a linear Riemann-Hilbert problem, or we could use something that's really built on doing infinite dimensional linear algebra. Going beyond that, we could use this other techniques for computing Wiener-Hopf factorizations like rational approximation, iterative methods, and there's this great review article with by some of the attendees in the audience. Possibly all the attendees, but I don't know if Mishuris or Rogerson are here. But anyways, okay. So how do we do Wiener-Hopf in a numerical way in the sort of simplest setting possible where our symbol is just tridiagonal? So rather than doing complicated symbols, we're trying to make it as easy as possible. Well, if I ask what the UL decomposition is, we can recast it as a Wiener-Hopf factorization, in which case we have an explicit formula in terms of exponentials of Cauchy transforms. So we plug in our symbol A of z into this formula, take its logarithm, compute its Cauchy transform, take its exponential, do the Taylor series around the origin. And in theory, that will tell us, well, here I'm imposing that the diagonal of u is always 1, so here we just want to know these three numbers. Essentially, this encodes those three numbers. Of course, this is sort of a silly way of writing 1, 2, 1 is the exponential of the Cauchy transform of log of some very simple symbol, and in theory it works, but actually because this is a degenerate symbol, it kind of breaks down, but anyways. So the question is, how do we effectively, in a numerical way, take this formula and get out 1, 2, 1, or whatever the UL factorization is for a general symbol? So the easy way to do this, or the natural way I should say, is take the logarithm and do a finite approximation using the FFT in a Laurent series. And then we can compute the interior and exterior of the Cauchy transform. That tells us C plus log A is this. This takes the non-negative entries in the Laurent series. This takes the positive. And therefore, we can recover phi plus and phi minus, do another FFT and compute these entries. And those tell us the entries of the U and the L. Okay. And this works, but it only works well if we're away from the continuous spectrum. So here are the number of coefficients needed to expand log of AZ, I guess I should have put minus lambda, but in this case it's a plus, pushing away from the continuous spectrum. And what we see is as we approach the continuous spectrum, the number of degrees of freedom we need in our FFT has to grow. And actually, as we approach the continuous spectrum, it just breaks down. Okay, so if we use the exact formula, so most people in the audience would consider this a solved problem because we have an exact formula, but in practical considerations on a computer, the exact formula is not so effective because it breaks down as we approach the continuous spectrum. It takes n log n, where it depends on the spectral parameter, and it also, so this one everyone would agree with, it doesn't work with block Toeplitz matrices, so block Wiener-Hopf factorizations. Okay. So another alternative is to recast a Wiener-Hopf problem as a Riemann-Hilbert problem. So, which I did a lot of work on numerical Riemann-Hilbert problems, so this was the first approach I tried when I found out about Wiener-Hopf and Toeplitz matrices. So you can take our Wiener-Hopf problem and just hit it on the left and the right by phi minus inverse. And so here we change this from what I would call a Wiener-Hopf to a Riemann-Hilbert. So again, we want something analytic inside the unit disk, analytic outside the unit disk. And the benefit of this is we can then write our inside and outside analytic functions in terms of a Cauchy transform, plug it in, and we get a linear singular integral equation. If we expand U in Laurent series, and again, focusing on the tridiagonal case, we get this very simple banded linear system that we want to solve. Now, hidden in this linear system is the original Toeplitz matrix we wanted to find the factorization for. So you might think we sort of got back to where we started, but now what we want is a UL decomposition, but we can use other factorizations in order to solve this linear system. For example, we can rewrite this as, say, block tridiagonal and do LU or QR or anything iteratively, and that actually works quite well. Or even just truncate and solve. So this works, but it has the exact same problem that, so the positive coefficients are actually computed exactly or with finite number of entries. The negative ones we have to compute more and more because we're not expanding psi minus, or phi minus, we're expanding phi minus inverse. So we've taken something that is a polynomial with 2 degrees of freedom, an affine function, and made it something that's rational, and therefore its Laurent series goes on forever. And numerically, we have this behavior where, again, we break down as we approach the continuous spectrum. Okay. So this almost is as bad as the exact formula. It's slightly better because it's now at O of n instead of n log n. I think these convergence rates are faster. So here we get 16 digits, where before I don't think we quite got 16 digits. And it works with block operators, but it still breaks down in the degenerate setting. Okay. So instead, we can think of an infinite linear algebra approach. What I mean by this is we can take our Toeplitz matrix and write it in this form where A is embedded inside itself. Suppose we know the UL factorization for A. We can pop that out. This is our new U. This is our new L. And since we don't have a huge amount of time, essentially we know this U is the same as that U. And therefore, embedded in this is sort of a system of equations. And actually, these are just saying, if I know A and L naught, I know U minus 1. If I know A1, I know L1. These are the entries in the U and the L. And so all I need to do is compute this L naught, which solves the quadratic equation, which we can solve exactly. Okay. So applying this formula to our example where we shifted it so it's actually outside the continuous spectrum. So it's an invertible operator. We can compute an exact formula, and we get A is equal to U times L. Without having to do anything iterative, we sort of just get the answer right away. Interestingly, we actually get two answers, but only one of them has bounded inverse. So this is sort of thrown out because these are unbounded. So this is sort of the answer. Or their inverse is unbounded. And the nice thing, this works for arbitrarily close to the continuous spectrum. Okay. So we can take this degenerate case and get these two UL factorizations, and only one of them is sort of, the bottom one has clearly unbounded inverse, where this is bounded if we use the right norms. So from a practical standpoint, for tridiagonal Toeplitz matrix, we essentially know the exact answer. We don't need to do anything numerical. The nice thing is it actually extends to the block case, so extends to the general banded Toeplitz case, because we can replace our equations, our things now are blocks, and L naught is now a matrix, and it solves this, what would be a quadratic equation, but now it's a matrix equation of this form. Okay. Which, when I started writing this talk, I was going to ask the audience if they've seen this and know how to solve it, but then I was reading my own blog, and in my own blog I had a reference to this paper that contains a solution to this matrix quadratic-like equation. So it turns out you can actually reduce this to eigenvalue problems. So, and again, banded block Toeplitz is always the same as tridiagonal block Toeplitz if we make the blocks bigger. So this gives an effective scheme, a numerical scheme for computing UL factorization. So what do we do? I'll skip that because we don't have a huge amount of time. So here is just an example of a block Toeplitz matrix, sort of similar to Schrodinger with periodic potential if we reorder in even and odd. And we can use this scheme to compute the UL factorization. Okay. Okay. So that would be what I would consider a more linear algebra approach rather than using the sort of analysis of Wiener-Hopf techniques. So let me move on to the QL factorization, where Q, now instead of upper triangular, we want orthogonal or more generally unitary matrices. So in the Toeplitz case, we want to compute a factorization of this is equal to an orthogonal matrix times a lower triangular matrix. Now these are Toeplitz apart from, in this case, the first entry and here the first column. So how do we numerically factorize this Toeplitz matrix as Q and L in infinite dimensions? Okay, so now we have less options. We sort of have an exact solution for the tail for the Toeplitz part. I'll gloss over it, but mostly I wanted to put this up here because I don't know a good reference, but it seems like something that would have been certainly done by the Wiener-Hopf community. So essentially, factorizing our Toeplitz matrix is equivalent to factorizing our symbol as Q of Z, where Q of Z satisfies this equation, and P plus is analytic inside. And taking logarithms, you can solve it very similar to the standard Wiener-Hopf technique. So this actually tells us the tail but it has the same flaws as in the UL, where it breaks down if we're too close to the continuous spectrum. And if anyone knows literature related to this, please let me know. Okay. So let's instead focus on our more linear algebra approach. And again, we can take our templates matrix A and write it with itself embedded inside. Assume we have a QL factorization for that and take that out, and we get this. Now, if A is banded, this B is sort of everything's in the bottom left of the matrix. So if we increase the size of this truncation, we get something that's block lower triangular. Okay. So this is just taking this matrix and making it sort of, making our truncation bigger and putting some tildes to take care of the fact that the entries are slightly different. But now we've reduced it to a finite dimensional problem, a finite dimensional QL, and hence, if we can do, hence hidden in this is QL itself. Okay. Now this again will have the exact same feature that we can use as to get a system of equations that tells us what the QL factorization is. So looking back at the tridiagonal templates case, and without loss of generality, we can make the superdiagonal just equal to 1. That infinity shouldn't be there. That should just be, we want to find A is Q times L. L has this form, as we saw numerically, which is templates apart from the 1-1 entry. And we can apply this to the bottom right of this matrix, and we get this equation here. And essentially what this is telling us is these entries that we don't know the D's or the L's, but they're fixed points of this finite dimensional QL factorization. So here are A's in our matrix. These are what we don't know, the D's. But if we knew the right answer, it would satisfy the property that the QL factorization of this 2×3 matrix gives us back the D's and the L's. Okay. So then we just need to solve that fixed point iteration. We can do this with Hessenberg. I'll skip that and get to sort of the conclusion. So effectively, okay, what did I skip? Effectively, we can solve this exactly as an eigenvalue equation. So we want a fixed point iteration of this. We can recast it as an eigenvalue problem and write these entries, the D's, in terms of our data A's. Okay. Now, there's a lot of questions here. One, do QL factorizations always exist? In the general setting, not just templates. No, not always. And furthermore, they're not necessarily unique. So if we go back to our bullhead templates symbol, we can compute QL and plot 1-1 entry of the QL. And here we can see it doesn't exist in this part of the spectrum, but does everywhere else. Whereas the transpose is sort of but here there's actually multiple QL factorizations. Okay. I'll skip the embedded eigenvalues, but you can use this to compute embedded eigenvalues too. And I think I'll stop here. What did I want to say? We can compute UL and QL factorizations. You can also do QR and LU. There's a lot of questions. We don't have a general theory of QL factorizations for operators going beyond just templates case. And really the ultimate goal is doing this in 2D. Okay. So I'll stop there.
Thank you very much for a nice talk. We have time for one quick question.
I'm not sure if it's quick, but you just flashed over your last slide. Do you want to say something on that yet?
Yeah, okay. So I wanted to motivate the connection with continuous Wiener-Hopf, which essentially Wiener-Hopf of a symbol is telling us LU factorization, where L and U are Volterra integral operators, one coming from the left and one coming from the right. Again, this was another thing where I assume it's somewhere in the literature. If someone can point me a reference to this, it would be nice. But it's just sort of cute observation. I don't know what it's useful for, but okay.
I can send you a reference for that.
Okay, great.
Okay, let's bring the speaker again.